not there yet. Yep, here we go. Now we are actually streaming. I can cut the video afterwards, so that's fine. Let me just close the window here, just a moment. So I'll start the webinar now. Some people joining. Let's just wait, I don't know, 30 seconds or so everyone can actually join in. So we're just awaiting maybe minutes so everyone can join here in the YouTube channel as well, and then we can start. Okay, so I will start. Well, hello everybody. Happy New Year. Welcome to the monthly edition of UCL Insights. I'm your host, Adriano Koshiyama. I'm a research fellow here at the UCL Computer Science Department. With the drive towards automation and digital transformation, now accelerated by COVID-19, research and development and deployment of machine learning systems continues to increase. AI is a high-impact technology that has the potential to revolutionize all areas of medicine, for instance, from patient care to data analysis and surgery. This UCL AI Insights event will explore the evolving critical field of AI in health. Joining this panel today to discuss this topic is Dr. Danielle Belgrave from Microsoft and Professor Parashkev Nashev from UCL, where they both will discuss a few difficult truths about what complex modeling can and cannot do in healthcare, and the right path to its application in the domain, with some focus on how we can ensure trustworthy and fair AI systems for healthcare. I'll just do a quick bio reading. So Danielle Belgrave is Principal Research Manager at Microsoft in the Healthcare Intelligence Group at Microsoft Research in Cambridge, UK, where she works on Project Thalia, which explores how a human-centric approach to machine learning can meaningfully assist in the detection, diagnosis, monitoring, and treatment of mental health problems. Dr. Belgrave's research focuses on integrating medical domain knowledge, probabilistic graphical modeling, and causal modeling frameworks to help develop personalized treatment and intervention strategies for healthcare. Welcome, Danielle.
Thanks.
The second panelist is Parashkev. Parashkev Nashev is a professor of neurology at the UCL Institute of Neurology and honorary consultant neurologist at the National Hospital for Neurology and Neurosurgery at Queen Square. His high-dimensional neurology group is funded by the Wellcome Trust to develop novel computational methods in the domain of neurology for predicting clinical outcomes and guiding therapy with individual-level precision. Welcome, Parashkev. Thank you for coming. So I will just open the floor to Danielle so she can make some initial considerations, and we can just kick the ball afterwards. Thank you.
Okay. I need to be able to share screen.
So I'm doing that. Yeah.
Okay. Great.
Thanks, Danielle. Sorry.
No worries. Right. Okay, well, thanks for that introduction, Adriano, and thanks to both you and Emery as well for organizing this panel. So I'll just have just prepared a few slides to give a 5-minute overview and sort of get the conversation started on AI and health. And I'll just provide a brief overview of some of the key ideas that come to, at least to my mind, when I think about AI and health along these 3 axes of research, practice, and innovation. And as Adriano mentioned in the introduction, currently I'm working in machine learning for understanding mental health in Project Talia. And for me, this is a huge area where we can have a lot of impact. When we think with mental health, 1 in 4 of us at some point in our lives would be affected by a mental health condition. So this research, practice, and innovation within the space of mental health and within the space of healthcare in general is something that's really important. And I think to set the context, I think it's good that we take a step back to think of healthcare within the broader context of the Sustainable Developmental Goals. So we can think of healthcare within this context, and the Sustainable Development Goal number 3 is to ensure healthy lives and promote well-being for all at all ages. And this has become even more relevant in the pandemic period, where before COVID, there were lots of shortfalls within healthcare. And we've been thinking of ways, how can we use AI to accelerate the access to healthcare and also accelerate just the landscape of healthcare as well. And with COVID, we've seen a big drawback in lots of areas of healthcare as well, where maybe we've had to prioritize COVID rather than looking at other healthcare areas. But looking at health is super important, and it's a great application for AI research as well. I just want to touch on some of the key challenges when we think of applications of artificial intelligence to healthcare. So I'm a machine learning researcher, and a lot of these are anchored within the fields of machine learning. So one of the big challenges of AI for healthcare is understanding heterogeneous patient populations. And a lot of the work that I do is on trying to understand how we can personalize healthcare interventions. And when you think of personalization, it's about getting the right treatment to the right patient at the right time. And what we realize is that not everybody responds to treatment in the same way. So how can we understand that underlying heterogeneity using machine learning approaches? So as Adriana said in the introduction, a lot of the work that I do is using probabilistic graphical models to understand patients' population level heterogeneity, so that we can understand within the same disease context, why is it some people respond to treatment and why some people don't, and how can we tailor interventions? Another huge challenge in machine learning and artificial intelligence for healthcare is that of generalizability. When we train a model on one particular population, how can we extrapolate to different populations, whether that's different ethnicities, different geographical populations? And this is a huge challenge within machine learning for healthcare as well. Causal discovery is another challenge. How do we know whether something's causal or associative? And within the context of generalizability and causal discovery as well, looking at model accuracy, there are other challenges as well, like data in the wild. So with healthcare data, we have lots of different data sources. So not only do we have heterogeneous patient populations, but heterogeneous sources of data as well. So how can we aggregate these heterogeneous data sources in order to get a meaningful context of a patient to personalize interventions? Healthcare data is messy as well, especially if we're relying on patient reporting. There's a lot of missing data, and this creates a huge barrage of problems for generalizability and how to apply machine learning within a healthcare scenario, in a real life scenario as well. And there are another two challenges are those of interpretability. How do you go from research insights to actual practice? And what does the interpretation of models mean in a real world context? And fairness as well. So and I think this is super important within the context of generalizability and heterogeneous patient populations. How do you make sure that algorithms aren't biased and that the solutions that we provide in a medical context are also fair to all people? So I think the title of this panel highlights one of the big challenges and at the same time a huge opportunity for research in AI for healthcare. And these 3 dimensions of research, practice, and innovation aren't just juxtaposed dimensions. But when we think about machine learning for healthcare, the reason most of us work in this space is because we want to develop technologies and algorithms that would have real-world impact. And this is the heart of the challenge. And at the same time, it's what drives us to work in this field. The question of how do we translate research into practice, into actionable insights that we can change the world of healthcare tomorrow. And through that real practice and real world application, through testing systems, how can we innovate and make those systems better? And in making those systems better, we can have a high impact and improve the lives of many. But this is a huge challenge to move from translating research insights from deep research using machine learning to actionable insights in the real world that has real social impact. So we can think of these three axes of research, practice, and innovation as three coordinates of discovery, human-centered solutions, and real-world impact. But achieving this in practice, achieving impact is not an afterthought. Context really matters. So as machine learning researchers, as people working on AI solutions, we need to think deeply of the clinical context and also the context of the patient as well, to find solutions that are patient-centric and that are specific to the problem. And this is what good science is about. It's about not working in silos as machine learning researchers, but also communicating with domain experts, whether they be clinicians, social scientists, or the human users of technology as well. And we need to do this merging of different schools of thought to develop a bigger picture. So even though with machine learning we use a data-driven approach, we also need to incorporate that domain knowledge to have a problem-led approach with the patients at the center of the solutions we develop. And that's it from me.
Thanks, Danielle. Yeah, let me just go back to gather review. Yes. Also, I guess everyone feel free to ask the questions via the Q&A option. I've got some questions via email, funny enough. And also, Prashkev, feel free as well to put up some questions, anything that you would like to ask. One thing that I'm very interested is the mental health angle. And I think mental health is one of those tricky areas that if you're developing some kind of machine learning or whatever solution, and I can think about chatbots and all kinds of things, is you have to access people's data to develop this type of product. So it's one of those areas that is very complicated because you're dealing with very personal data and also very sensitive information. Is there any projects that you've been part of that, and how did you manage to mitigate or deal with these risks?
Yeah, so I think, yes, healthcare data is sensitive data. This is personal information. But I think as well, the legislation that we have in place is very helpful for this context. So we can think of GDPR, which came into effect a couple of years ago. And for me, GDPR is all about empowering patients and empowering people, because it's not just healthcare data. There's lots of different types of data. And we know that GDPR was born out of the context of realizing we need to foster privacy and also help people to know how their data is being used. So I think one of the big things about GDPR is making very conscientious within the public that you give consent for your data to be used for certain things. But also the flip side of the GDPR as well is the protection of individuals. So whether it's through the use of browsers, that you are protected as an individual and your privacy is respected. And whether you give consent for that to be used, you are the owner of your data as well. So I think one of the really important things is making very intentional and explicit this thing of consent of data, that you are the owner of your data. You can require your data to be deleted at any time. And I think this is important as well. But yeah, I think this is an important point.
Yeah, that's really good. There's a question in chat, sorry, in the Q&A from an anonymous attendee. They're asking if you could give any specific example of a problem that you have tackled using probabilistic graphical models.
Yeah, so a lot of my previous work, it has been in asthma and allergic diseases. So probabilistic graphical models has actually been the bread and butter of a lot of the work that I've done. So I started working in artificial and I would say machine learning for healthcare within this context of asthma and allergic diseases. So I can give two specific examples. One is looking at the development of asthma as a phenotype. So with asthma, when I started working on this, it was about 8 years ago, where we thought asthma is an umbrella term. So what the clinicians were observing in the clinic is that not everybody responds to treatments. Even though they have a diagnosis of asthma, they're not all responding in the same way. So using probabilistic graphical models, what we did was we looked at longitudinal data. So we looked at data from birth to when children were 11 years old. So the hardest time to diagnose asthma, by the way, is during childhood. You don't officially make a diagnosis until you're 7.5, I believe. And so, but you can give medications or interventions. So using probabilistic graphical modeling, what we did was we took all of the data from healthcare records of 2,000 children, and also we asked these children, or their parents rather, questions on a yearly basis to see what was the progression of their symptoms over time. And using probabilistic graphical modeling, we were able to infer a latent structure based on those phenotypes of symptoms over time. So we identified 5 different subtypes of asthma. And within those subtypes, we were able to further identify that there are 2 groups called asthmatics, and there was one group that responded to treatment and another group that didn't respond to treatment. And then based on these subtypes, we were able to find genetic markers as well. So there's a lot of work that I've done on this area that we've published as well on understanding asthma heterogeneity. There's also some other work trying to incorporate probabilistic graphical models within a causal context. And this was looking at how allergies are developed during childhood through multiple symptoms. So this was some work we published in PLOS in 2014. One of the things I found asthma very fascinating, but I find mental health even more fascinating just because of the scale of mental health. You know, I was saying 1 in 4 at some point in our lives will have a mental health condition. So for me, a lot of the work I've done with probabilistic graphical models is around understanding patients' heterogeneity. And the reason we want to understand that heterogeneity is so that we can personalize interventions, because we know that people manifest symptoms differently over time. And I think this is even more pertinent with mental health. So last year, we also published some work looking at different behavior types in terms of how people engage with digital mental health technology. Because we know that cognitive behavioral therapy is effective, but we also know that there's a high rate of dropout with CBT. And we wanted to investigate what's the impact of engagement on mental health outcomes. So we developed a hidden Markov model based approach for these for different types of engagements, and the details of that have been published in JAMA last year. So I think probabilistic graphical models is a really useful tool, one for disentangling causality within a healthcare context, but also for understanding patients' heterogeneity. And it's very much a tool that I think can be used a lot for understanding personalization of interventions, because if we can disentangle this heterogeneity and encode latent structure within a clinical context, then we're one step further towards getting the right treatment to different subgroups of patients.
No, that's very nice. One thing that I'm always puzzled is just because I really don't, it's not really my area of practice, is one thing that I know is that you have this type of observational studies and have this controlled experiments that you do when you're testing a medicine or anything like that. And I guess you're always, even if you're doing machine learning or whatever you're doing, you're always also in the same, you have to use one of those 2 frameworks to understand. Or is there anything else that kind of machine learning in a way created a new framework out of these 2 paradigms of investigation?
Yeah, I think this is really a fascinating area of research, and I can talk about this at length. But I just want to highlight, this question of the distinction between observational studies and randomized controlled trials. I would say electronic healthcare records is another type of data, but I would also put that within the umbrella of observational studies. And these are very different scenarios. So, for example, in observational studies, it's very hard to it's very hard, but I would say it's not impossible to disentangle causality within that context. Within randomized control trial, you have a control setting, you know when things occur, when interventions are given, so it's a lot easier to measure causal effects. But within an observational trial, that's within an observational study where you're just looking at what happens in a population, it's a lot more challenging. But at the same time, with observational data, because it tends to be data in the wild, it's a lot more, sometimes it tends to be richer, even though it's not in a control setting. So you do have a lot more scope for discovery within that setting. But I think one of the challenges is how do you combine these? I think the optimal is looking for ways to meaningfully combine real world data settings with randomized control trials in order to optimize discovery within these landscapes. But I think this is a huge area for impact.
There is a question here which is related to the patient data, which I'll probably put to you both at the end, because I think you both have something to say. But if you'd like to make any considerations about it right now, which is related to patient data, how do you deal with incomplete data in healthcare, trying to make the data as representative as possible. I think I will leave it to these questions maybe to the end, because I think you both have a lot to say about these two issues. One thing that I'm very keen to hear is the frontiers you're seeing on the mental health issue. There's a lot of wearable technology. In finance, people call alternative data, which is basically data coming from, anything and not economical. So data coming from Amazon, data coming from Google Trends and things like that. And sometimes I think that Google's and Amazon probably knows more about our mental health than actually we are aware of. What is the frontier now in the mental health saga on healthcare?
Yeah, so I think this is a very hard question. So the sort of frameworks that I deal with aren't directly in this space. I do agree that data is very ubiquitous, but also I think that we need to frame. I think there's a lot to be said about framing the questions we want to work on very carefully. And thinking, what is it we want to achieve with the questions we look at? And when you think of what are the questions you want to achieve, or what are the solutions you want to achieve, I think in the sort of 5-minute presentation, I said achieving impact is not an afterthought. I think also ethics is not an afterthought as well. That the questions we ask and the way we look at data has to be ethical. So. I think that's why, coming back to the question of GDPR, it is super important that there are these systems in place to make sure that patient data is protected and that data is properly de-anonymized as well. But also that there's a lot of clarity in what are the sort of questions that we're looking at and what are the implications of that as well. Yeah, so I do agree that health data is ubiquitous. There has been a lot of work around how you can detect different conditions through web searches and these sorts of things. That's not something that I necessarily deal with. I think this is a very hard area to know where are the frontiers and what are the solutions we should be looking at as well. And I think this is something that has huge potential, but we do need to think very deeply about ethical considerations as well. And that's important. And it's not just up to the ethicists to do that. I think it's everybody's responsibility to think of the implications.
Yeah, that's a very this final remark I think is very important, particularly when you and I know I haven't been through that because most of the data I've dealt with was not personal data. But I have a lot of friends who are doing work with some medical information like genomes and all this stuff, and also X-rays, and sometimes they'll even make interventions through wearables, and they would have to go through a bioethics or ethical review or something like that that university has. But it's like it's a separate commission that kind of analyze that. And you're alluding to say, this question shouldn't be just resolved by the ethical commission. It should start from you. So how do you see this trend happening actually? Instead of having this oversight committee that decides what is ethical or not, to actually coming to the team that is developing it. How do you see this trend moving?
So I don't know in terms of general trends, I am not sure, but I can talk about what my particular approach is. So one of the things that I value highly is interdisciplinary research. So I'm a machine learning researcher, but I work with lots of different people before we even get to a review stage. So I work with clinicians, designers, but I also work with social scientists who think of the impact of technology on users, and within that they think a lot about ethics as well. So this has to be a very important part of my way of thinking, and I think a lot of teams do this as well. And there's more and more awareness of not having ethics as an afterthought, or not just sort of trying to sort through the ethical considerations by yourself, but really working with a team of people to understand those ethical considerations as well. And then an external review is very useful as well for helping to identify blind spots, to see whether there's something that's been missed or something like that. So I think these are really important considerations.
Okay. There is some other questions of which I think has to be for you both to answer. So I would just now open the floor to Parashka so he can make also his initial considerations. And thank you, Danielle. I mean, you'll be around, and we have a fun discussion at the end as well. Could you make him the host now?
I don't seem to have access yet.
Yeah, Danielle, could you make him the host? I think you have the.
We'll just alternatively enable sharing.
Yeah. So the awkward moment on Zoom.
Yeah, works.
Thank you.
So I hope you can all see that. So I think the first thing to say is that I think it's useful to remind ourselves how medicine is done now, at least how it was done before complex modeling came along. The way in which we think of individuals is essentially as noise that's superimposed on some kind of group average. So for example, here we have a fairly homogeneous cohort. These are all the cardinals of the Catholic Church. And essentially we'll take one particular individual as being merely this, with some noise super added. And because we're accustomed to the natural heterogeneity of faces presented in that way, it seems totally absurd. And it seems even more absurd if we consider what is the current gold standard for how interventions are guided in medicine currently. Imagine that our cardinal had some kind of illness here, simulated with a particular unpleasant pressure shock filter. The way that medicine treats its repair is as a transplant based on information from the average of the population, producing the result that is depicted on the far right. Now, because it's a face, we can see that this is obviously catastrophically poor as an approach. But because we're not naturally aware of the heterogeneity of the rest of the body, of course there's no reason it should be any different from the face, this seems to us a perfectly reasonable approach. But it isn't. And what we have to remind ourselves is that actually what we want to do is to compare individuals to the centroid of their neighborhood, essentially to reduce the heterogeneity down to the intrinsic structure within the variability of the data. So the individual then is approximated to the neighborhood of that particular person. That's how medicine should be. That's how it should always be. And so the introduction of complex modeling isn't really something that is a luxury. It really needs to be something that lies at the core of medicine itself. And in fact, the task here is to make medicine less mechanical than evidence-based medicine has already made it, by making it a lot more like a far richer, far more nuanced decisions that human beings make, but of course to maintain the kind of objectivity that we would like to see in anything that is being deployed in an evidence-based fashion. So in a sense, AI here makes our intelligence less, not more artificial. And it is something that brings us closer to what medicine should always have been like. Now the question is, why is it so hard? Danielle's been talking about biological heterogeneity, which is, of course, probably the most important aspect. And we should remind ourselves that biology is under pressure to diversify, but also to be opaque. So heterogeneity here is not an accident. It is something that's actually part of how biology works. The reason for this is that, of course, we have no idea. Biology doesn't know what is optimal, and so it has to spread the variety of possible solutions as widely as it can, and also it has to keep them opaque, because otherwise an adversary, perhaps predator or a pathological agent, could find it very easy to circumvent. We should also remember that not only is biology heterogeneous, so are the instruments that we use to probe it. We tend to think of brain scans, for example, any other kind of imaging, as being a bit like a photograph. But actually, it's a representation. It's not a surrogate for the object. It's distorted in all sorts of complex ways. It's really much more like a painting than like a photograph. And so capturing instrumental heterogeneity is as important and can be as difficult. And then there is the notion of causality, how it is that these biological mechanisms operate. It has been natural, really, since the history of medical science, to try to explain everything in serial, relatively simply organized terms. And the reason we've been satisfied in that temptation is because around the edges, medicine is relatively mechanistic. And there are one or two things that do appear simple. But actually, the fact that we've had so little success in many of the major diseases over the past decades, really centuries, probably is a reflection that causality here is complex and can never be reduced to any simple mechanism. And why should it be? After all, its task is not to be easy for us to understand. Its task is to be flexible. Flexibility and complexity go hand in hand. So what should we focus on then in deploying complex modeling to these tasks? Well, at the moment, the focus tends to be very heavy on prediction. We all know, in fact, probably the first examples we can think of when somebody asks us about examples of healthcare AI, these are predictive systems, because in a sense, that's probably the easiest thing to do. And of course, people are interested in inferential questions, trying to describe what the underlying structure of the causal dependence of what is observed is. But really, the focus of medicine is prescription, it's intervention. What we try to do is not simply to predict what will happen to somebody, but to change it. And that, of course, requires much more complex models, and it requires a great deal of thought about how one can describe the space of causal possibility, so that then one can not only model what happens or what might happen, but various counterfactual possibilities conditional on intervention that we can make. So, in summary, I think an important distinction that one has to make is between systems that are by their very nature mechanistic, by their very nature serial, that can be described in simple terms, and ones that are deterministic, just as deterministic as something like a watch mechanism, but whose complexity makes them impossible to model in any simple way. And in reality, medicine is much more like meteorology than it is like horology. And despite the fact that we try to think of it in simple mechanistic terms. And the amount of computational and algorithmic innovation that we throw at it really ought to match and indeed exceed what is currently thrown at the weather. And if the UK, for example, currently thinks that the 1 billion supercomputer is a relatively modest installation for weather prediction, it is strange that we don't believe the same in medicine. So I'll pause there, and perhaps we can think about some of these details.
Thanks, Prashad. I mean, it's always very inspiring presentations. And one thing that I remember we discussing a few months ago was really this ideological, maybe not ideological, it's probably old science versus new entrants, new kids in the block, which is the gold standard, as you point out, versus what personalized healthcare via AI could provide. How is the state of the war as we speak? Is it tilting more to one side, or maybe the old side still winning?
I think I suppose the field is polarized. There are those who believe that AI is going to be our savior, and then there's those who are deeply skeptical. I think what's striking is that very few actually understand what the real issues are. And I think part of the problem is the reluctance even to attempt to understand them or to confront them, because it's intuitively so much more attractive for somebody of a scientific bent to have something specified in terms that are easy to explain, that appear to be easy to test, that are just natural, that reduce what we observe into a mechanism. It's just, that's how scientists tend to think. That is how we are taught. And I mean, if you think about it, it's commonplace to say that you have to have a hypothesis in order to have any kind of meaningful research program. Whereas really, to say that you have to have a hypothesis is essentially to say that you have prejudged the range of possible answers. This idea that hypothesis generation is something that we ought to be doing intuitively, borrowing all sorts of analogical frameworks, such as, it's very common, for example, in neuroscience, to try to explain the brain in terms of computational terms. Essentially, that's just reifying concepts that are drawn from the mechanistic world of computing that need to have no purchase on what really goes on in the brain. So I think actually the main problem is a kind of, it's almost an emotional one, to accept that this is a very different realm, that satisfying our vanities cannot be the number one priority. What we need to care about is what is it that we can actually do for our patients. That's our task. And if it means deploying black box machines that no one can understand, well, so be it, provided they generalize, provided they work, then it's fine. My feeling is that certainly amongst the medical community, as soon as there is sufficient evidence that these approaches succeed, I think there will be a much more rapid shift towards accepting it. Because clinicians are practical animals. They care about what happens in the real world. That's their focus. And if something works, yes, they will usually be very skeptical, if they should be. But if it works, if it's proven to work, then it will be adopted.
Yeah. Everyone feel free to ask questions, Danielle, Q&A as well. I'm going to go off topic, then I'm going to come back to the topic. And the question is going to be also for you both. Just quickly, because Prashkev is here, I'm very interested on the brain for some reason. And I think a lot of people in in machine learning, etc., is interested in brain because, well, most of the learning stuff that we do, supervised learning, unsupervised learning, transfer learning, etc., is all about learning, and we hope our brain or what we're doing kind of replicates what's happening on our brain. Is there any, you're fully aware of these things, is there any learning paradigm that we actually have not managed to accomplish or have done a good job, or is there anything hidden or secret still from us?
Anything more hidden or secret about the brain?
Yeah.
I think everything about the brain is hidden and secret.
Okay.
The idea that we understand anything about neuroscience, I think is more or less far-fetched. I mean, what we have is sets of rationalizations of biological phenomena. There is, of course, all sorts of points of fact. The behavior of neurons in certain circumstances can very clearly be described, there's no question. And there's certain low-level relationships and particular subsystems within neuroscience that can be reasonably well described. The problem is that what we have to ultimately explain is the operation of the animal as a whole, which means we have to look at the integration between all of these multiple elements, this vast diversity of physiological processes. And that's the challenge. The complexity of that is so immense that if you attempt to fit your little theory to it, what happens is very easy to come up with exceptions, which basically tell you that the theory is, well, it's just a kind of a reification of a very coarse and very vague description of what we think is going on, but which is not really compelled by the facts themselves. I think that's the problem. Is there going to be a point at which we will have anything that one could really seriously call understanding of the brain? Maybe, but I doubt in my lifetime.
Oh, that's interesting. Yeah.
I mean, I think that's different from being able to make useful predictions. Of course, we do that all the time. And in fact, my research program is focused on being able to decipher the relation between patterns of brain damage and patterns of underlying function and then the outcome, and in particular how I'm able to change it in order to improve. But I don't think those are properly described as explanations. I think those are models that have specific tasks, maybe prediction, maybe prescription, maybe whatever. And those tasks will be asymptotically satisfied. So we'll get better and better and better, but we're never going to have a perfect understanding, a perfect description of any systems, because each one is unique. Every single individual human being is unique, and they can be mechanistically unique. The uniqueness needn't be merely superficial.
Yeah, I think sometimes we just don't want to believe in the uniqueness, just because maybe sometimes just because you're looking at a spreadsheet and you're able to put up a lot of individuals in the same spreadsheet and they kind of share common attributes, and then you do the simplification and then you think they're actually
I suppose it's because there's obviously a commonality of function, so we all tend to be able to do the same things, right? Because our powers are shared. But it's exactly like training a very complex deep net. You're going to get the same input-output transformation if you apply the same loss or whatever, if you're pursuing the same objective function. But the way in which one architecture solves the same problem to the same level of fidelity, the same pattern of performance, may be radically different. And even within the same architecture, it's the way in which the network might be configured. And when you look at the brain, well, the brain is also not a fixed network, it's a dynamic network, it's changing all the time. And the patterns of heterogeneity that exist are very, very substantial. We can already say that they're very, very marked. So there is no reason for the implementation to be the same, just because the input-output transformation is.
Interesting. A question to you both, and I'll start with Rashket because it's a discussion we had also a few months ago, where we were talking about the on how can we search for more actable treatment. And then we were talking about what usually people in the bias and discrimination / fairness literature tends to do, which is in most cases you end up having to sacrifice accuracy and performance of the model in search for more equitable allocation or treatment. And this happens particularly in areas like recruitment and even credit scoring and facial recognition and so on. You have disparities across groups that comes up. And then with the discussion, then you said something that is very important, which is in healthcare, it's a different context. Crippling the model, as you put it, is a bad idea because you end up hurting people. So how do you go about? And it should be, in fact, trying to improve the model for everyone at the same time. Can you elaborate a little bit more about your question?
Yeah, I mean, I think the most important thing is to recognize that in medicine, we're not trying to treat everybody equally, because obviously we don't want to give everyone the same treatment. That would be the definition of bad medicine. What we need to do is to give everyone the same opportunity to achieve the best possible outcome. And so our focus is always on outcome and not on how we get there. If one person needs one treatment and that treatment is specific to him or her, then that is the treatment that we should try to target. We should give a generic treatment just so that everybody is treated in the same way. So that then becomes a question of how we define what is optimal for an individual. And that becomes a question of how well we define the structure, the underlying heterogeneity. And so what we need to do is to find the best possible representation of what is the variability and responsiveness to particular treatment in the population, and make sure that we've got models that are able to allocate treatment as accurately for each subcluster as we can. So it seems to me the priority here is to achieve individual level fidelity, and also to have a measure of how good confidence in that fidelity is for each particular cluster, so that then the intervention is not, oh, we make the model worse for everyone, but well, here we've got a cluster that's insufficiently characterized. We go out and get more data. That's what we should do. The object of medicine is always the individual patient. Public health is a subset of medicine. It's not that veterinary medicine is a subset of public health. When I have a patient in front of me, I'm answerable to him or her here and now. I'm not answerable to populations. And that's why our models have to reflect that ethos. Focus on the individual is the priority, and other considerations flow from that.
Anything you want to add, Danielle? Or
so I was really happy to see Prescott's presentation, and I think that the assessment he's just given is spot on. I think there are many different angles, but one of the ones that I strongly advocate for is precisely using machine learning to understand this underlying heterogeneity and moving away from allocating interventions for average effects, not maximizing the average, but trying to maximize the subgroup. So this is I think this assessment is spot on. If we can understand that heterogeneity, then we can better target interventions. I think one other area that we can highlight as well is there is a need for diversity in data sets. From a public health and population health perspective, it is known that it is a challenge to collect diverse data sets. Recently, I've been on a panel looking at with different researchers from mental health, and I think this is one thing that really struck me. There was one person on that panel who was looking at collecting mental health data specifically within the Black community and the Indigenous American community. And these are huge groups that at a general population level, they are hugely underrepresented when it comes to data collection. And this process of data collection is a whole process of building trust. And I think the data collection process is, we really can't underestimate or undervalue this, that it's a lot of building trust as well within a community, and also understanding what are the questions we want to answer. And this is one way of us helping us to evaluate different levels of heterogeneity as well, by trying to understand the what is happening on a population level. Yeah.
Yeah. There's a question, I think, which applies, I guess, to you both, because you are in different organizations, which is the question from Christopher saying explainability, and I think it means more transparency. He thinks that transparency disincentivize commercial organizations, and he's pointing out to Microsoft, but I would even say Google Health and some others, from conducting research in the area, in these areas. That there's a question he's putting forward. And I think the questions maybe can be applied to you both. And how do you see this collaboration between industry and academia, and the different types of transparency that you need to put in place, or IP, etc.? Does it make harder for you to actually put out some research piece or advance the research in the health space? We have seen a lot of benefits in other space, for sure. But what about health in particular? It is different.
Perhaps I can start. I think we need to be clear about what it is the hospital can and cannot do. Hospitals are never going to make their own MRI scanners, for example. Right? We're never going to make our own drugs, and so on and so on. But on the other hand, it seems to me that, as I've argued, complex modeling really lies at the core of what medicine is. And so it doesn't seem to me right that this should be something that we should be outsourcing wholesale to external organizations. The correct model for interaction here ought to be one where enterprise partners with expertise in machine learning, IT, etc. After all, these models have to be embodied in software. Work together with clinicians to produce systems that are embedded within hospitals. And that also greatly simplifies the task of handling sensitive data, because if the data stays entirely within the confines of the hospital, if it never leaves the hospital environment, then everything becomes much safer. And as the collateral, the task of implementing models that act on that data then becomes much simpler, because everything happens internally. Interoperability, the maintenance of systems, everything, all these problems then become simpler. So my view is that what we need to do is we need to embed these frameworks within the hospital environment. They need to become part and parcel of healthcare delivery. And crucially, they're not pieces of engineering exotica that you're supposed to add, that you might be inclined to add as a kind of jewel for super sophisticated healthcare systems. This is actually something that every hospital should have, because this addresses the fundamental problem of medicine, which is how do we descend as closely to the individual as we can with information that is gleaned from many, many people.
Do you want to add something, Danielle?
No, I totally agree with that assessment. And I think one other thing I'd like to highlight that Paraskav said before as well is this idea of, I think this is where collaboration becomes very important. And earlier in your presentation, you were saying that clinicians are very practical. And as a machine learning researcher working with clinicians, I think it's really, once you sort of crack this problem from a machine learning, once the machine learning researcher sort of cracks this problem internally of what is clinically useful, very often that helps a lot with transparency and interpretability as well, because there's a lot more buy-in from both perspectives, both the clinical and the machine learning perspective of what is a meaningful problem and why we need to solve this problem. So I think very much building problems, or rather building solutions that are immediately applicable, it becomes super important for the context of interpretability and transparency as well.
Excellent. Which I think is probably the last question of the day, which is the question going back to the beginning, which was a question about data and handling personal data and missing incomplete data in healthcare, the data collection process and having to be representative, etc., etc. So it's kind of the data issue. Do you have any good practices there, one or two principles that you follow when you're actually doing your research or when you're doing any application that you would like to share, trying to tackle these issues of trying to be representative or dealing with missing data or dealing with enriching the data that you're dealing with?
I mean, I would say that because the way that the problem is set up makes any solution asymptotic, and because we're not interested here in what might happen on average, every single patient counts. A model whose performance is 85% is better than a model whose performance is 84% correct. There's no reason ever to use the one that's less correct, right? This isn't conventional statistics. So it seems to me that the limit should always be feasibility. And I see no reason we should not always demand fully inclusive data sets. It's a waste from every perspective, including a moral perspective, for data to be collected and not used. So every single datum that's collected in a healthcare environment should be made to work. And it should contribute to the way in which the system operates as a whole. And the only way to do that safely is to do it, I think, within the confines of the hospital, in systems that are under the control and the governance of clinicians, of the healthcare unit. So no data leaves the hospital environment, and at the same time, everything is analyzed together. Of course, that can be done with irrevocable anonymization in place, so that the risk is further minimized. And of course, we can limit the number of inputs to whatever is necessary. But the most important thing is to realize that sampling is always going to degrade the quality of the model that you end up building. And so it's never, data is never a bad thing. I know there have been arguments in the literature about situations where too much data might actually be bad, but that merely tells you that the algorithmics are poor. You know, theoretically, there can never be such a thing as bad data. And so we should always maximize the amount of available data, and we should do that by embedding the analytics within the clinical process.
Yes. Daniel?
Yeah, I totally agree with this point of maximizing information utility. I think that's really that is really important. I think, like, if I was to give a top tip in terms of sort of data handling, there's so many angles that you can tackle these problems from. I think it's always important to think of scenarios that you're trying to solve in an end-to-end perspective. So think with the end in mind, what are you trying to achieve? But in achieving that as well, it's really important to work in teams. So working in teams of people who have different perspectives of the data. So with clinicians is the obvious one. I mentioned earlier, working with social scientists as well. But I'd also say, as was highlighted earlier, the point of working with good governance teams as well, that working with expertise in what is good data governance as well is super important. And then there are lots of problems with data in itself. So if you look at context within missing data and just sort of getting to know the data, I think very often these are things that you need to do hand in hand with those aspects of data governance and clinicians and ethicists as well. So it's a process where everybody should be involved, and knowing how to collaborate and when to ask questions for feedback from machine learning models as well is super important. So being able to communicate context quickly and sooner rather than later is a golden tool.
Absolutely. You can avoid big mistakes. Instead of doing the whole project with a faulty data set, you should just maybe should start having a conversation with your team and seeing if you're doing the right thing. I would say that on this last note, I would like to thank Danielle Proshka for the fruitful participation and insights provided. Happy New Year to you both, and I hope you both have a great New Year ahead. We are still under COVID, and apart from Danielle, which is in a very sunny place, I think me and Proshka, we're both in lockdown London. So, but yeah, looking forward to just sunny time as well over here. So. Special thanks for America Zin for the coordination and content curation. Thanks for the UCLA Center, Computer Science Department, Faculty of Engineering, Innovation Enterprise for sponsoring our activities. Please subscribe to the UCLA Center YouTube channel and Twitter page. Follow the UCLA Insights LinkedIn webpage as well. See you next month, where we're going to discuss the legal aspects of AI. Goodbye and see you all soon. Thank you, Danielle. Thank you, Prashka.
Thank you so much. Thanks. Bye.